Welcome to MMA, your Mixed Model Academy. In part 2 of this series of tutorial videos, we learned how to accommodate the correlation structure of a random coefficient regression within MMA. In this video, we'll learn how to model the correlation structure of spatial data. Mixed effects models provide a powerful tool for modeling temporally or spatially correlated data. The goal of correlation modeling is to describe how the lack of independence between measurements changes as the separation in time or space between them increases. MMA offers several choices of correlation structure. The simple correlation structure, CORE, also known as uniform correlation, assumes that the correlation between measurements is constant, regardless of how far apart they are. The autoregressive model of order 1, AR1, allows the correlations between measurements to decrease as the separation between them increases. The most flexible correlation structure is the general correlation structure, CORE-G. It allows a separate correlation for every pair of measurements. The general correlation structure can be used for both equally and irregularly spaced measurements, whereas the autoregressive correlation structure should only be fitted to equally spaced measurements. Finally, MMA also offers the identity structure ID. This assumes that observations are uncorrelated or independent of one another. In part 1 of this tutorial series, we saw how to accommodate the correlation structure of repeated measures data. Let's now look at how to model spatial correlations between observations in 2 dimensions. The need to model spatial correlations occurs when the experimental units are laid out in a grid, for example in a field trial or greenhouse, and experimental units that are closer together experience more similar environmental conditions than those which are further apart. In this example, we're going to look at a spatial analysis of a field trial to compare the yield of 25 varieties of barley. You can download the data from the global project Slate Hall Barley Trial. The trial design is a balanced lattice square with 6 replicates arranged in a 15-column by 10-row grid of plots. Let's start defining our mixed effects model by populating the form with the response variate yield and a fixed effect for variety. The random model should include the terms involved in the allocation and randomization of the varieties. Failure to include the random terms involved in the allocation and randomization of a fixed term will result in the wrong denominator degrees of freedom being used to test the fixed term. For this trial, the allocation of the varieties to positions in the field depended on the blocking structure of the balanced lattice design. As each replicate has a block structure of rows crossed with columns, our random model must contain rep plus row within rep plus column within rep. Now let's model the spatial correlation, which is the lack of independence between experimental units due to spatial proximity. For the 2-dimensional spatial data set, the correlation structure is fitted to the residual row by column term, where the combination of the row and column factor represent unique positions in the spatial grid. By default, the variance structures for both row and column are set to ID, which would model the residuals as being independent. Spatial analysis can improve the estimation of the fixed or random treatment effects by modeling more accurately the spatial distribution of the residual effects. In most cases, it's reasonable to expect the correlation between pairs of experimental units in the spatial grid to decrease the further apart they are. Such a correlation pattern can be modelled by fitting an autoregressive model of order 1 in the row and column directions. This corresponds to an AR1 crossed with AR1 separable correlation model. Measurement error, also known as a nugget effect, is often needed to correctly represent the variability over the spatial grid. That is, the data may be more variable than what can be accounted for by the spatial model alone. Measurement error is allowed for by including an additional random term that indexes the observational units. MMA automatically creates this term for us, a factor called units. Now that our spatial model is completely defined in terms of the fixed and random models and the residual correlation structure, we are ready to click Generate to produce executable code. Thanks for watching Part 3. If you want to learn how to create other types of mixed models, check out our other videos, or if you need specific help, please contact support at mixedmodel.academy.